Hey guys, Miss Farron here. Today we're going to go ahead and look at Unit 7, Notes 5. We're going to look at independent versus dependent events. So we're going to use kind of what we looked at yesterday with the probability, and we're going to have to find multiple probabilities, determine if they are independent or dependent, and then multiply them together. So let's review what we looked at with basic probability. For A, we want to find the probability of getting a 2 on a fair number cube that is rolled once. So remember, on a fair number cube, the numbers we're looking at are 1, 2, 3, 4, 5, and 6. And when we find probability, we're finding what we want out of the total number of options available. So when I'm finding the probability of 2, I want a 2. Well, there's only one of those out of a total of 6 different options that we have. So when I plug that into my calculator, remember we do 1 divided by 6. And then we round to the third decimal, so you get 0.666, or 1666, but we would write that as 0.167. So now I want the probability that I'm going to get an even number. Well, my even numbers are 2, 4, and 6, so there's 3 even numbers out of 6 total possible. If I reduce that down, I get 1 out of 2, which as a decimal is going to give me 0.5. Last problem, I'm looking for the probability of getting a prime number. Remember, prime numbers are numbers that have only 2 factors, so only 2 factors. So if I look at my list here, 1 is not a prime number because 1 only has 1 factor, 1. So 2 is a prime number. 3 is a prime number because it's only 1 and 3. 4 is not because my factors of 4 are 1, 2, and 4, so that has 3 factors. 5 only has factors of 1 and 5, and then 6 has 1, 2, 3, and 6. So I have 3 prime numbers on a number cube out of 6 total. Again, that gives me 1/2. Reduced to a decimal is going to be 0.5. So now I'm going to change it up a little bit. I have a fair number cube that is rolled twice, and I want to find the probability of getting 2 4s. So if I'm rolling it twice, I'm going to have 2 separate probabilities. I have the first event, so the first roll, and then the second roll. So in the first roll, I want to get a 4. Well, there's only one way I can get a 4 out of 6. Now I'm going to roll that dice again. It's not like the 4 disappears. It's still on that dice. So if I roll it again, I still have the option of 1 out of 6. And when we are doing this today, when we're finding multiple things and you see the word, I want them and, or both, or all, these keywords are going to tell me that I am going to multiply. We want to multiply them together. So this is basically getting a 4 and a 4. So I'm going to multiply these together. And when we multiply, you multiply straight across, not cross multiplying. We're multiplying straight across. So I'm doing top times top, which gives me 1, and bottom times bottom, which gives me 36. Plug that into a calculator, I'm going to get 0.028. Now I'm going to roll this number cube. I'm going to roll it twice, and I want the probability that the first time is a 2, and the second time is a 3. So first time being a 2, there's one way I can get a 2 out of 6 possible. Then I'm going to pick it up and I'm going to roll it again, so there's one way I can get a 3 this time. We're multiplying them together, so again I get 1 out of 36. Which just like before was 0.028. Last example here, I want to get a probability of a 1 and then any other number. So we're still rolling this dice twice. Probability that the first time I roll it as a 1 is 1 out of 6. And then the second time I roll it, I can get any number and I'll be happy. So there are 6 numbers and I can get any of them. So it would be 6 out of 6. Again, we're going to multiply straight across. So 1 times 6 is 6. And then 6 times 6 is 36. If I reduce that down, I get 1 out of 6, which as a decimal is 0.167. Remember to round to that third number. So here we're going to look at some new terms. Let's first review probability. We kind of already looked at it, but remember, probability is the number of successes divided by the total number of outcomes. So what I want, how many ways I can get what I want, divided by how many total things there are. Now we're going to use this and we are going to determine if they're independent or dependent events. And what you need to keep in mind today is I'm going to ask you to find the probability of multiple things. Again, you want to keep those key words. When you see and both, or all, we're going to multiply these things together. So these words mean to multiply. That's going to be really important for you to remember that when you see and, especially this one, this is a really big one, and means to multiply in math. So when we're looking at independent events are events, the first event has no impact on the result of the second event. So you're going to see things like if I roll a die for the first probability and then I draw a card from a standard deck, rolling a die and a standard deck have nothing in common. So these have no impact on each other. Another thing that's really going to be important for us to see, when you see with replacement, this tells me they're independent. Okay? Dependent events is when the first event impacts the result of the second event. So if I draw an ace and then I draw a 4 from a standard deck without replacement, that is such a big word right there, without replacement. Basically, that means the number on the bottom of my fraction, the total outcomes I have, are going to change. If I take an ace and then I put it in my back pocket and then I draw a 4, I only had 51 cards to draw from that second time. So another thing you can think of is when your denominator changes, then it's going to be a dependent. So if that bottom number of your fraction is going to change, your options, total options you have is going to change, then it's going to become a dependent event. So for these next couple, we just want to determine if they're independent or dependent. So looking at number 1, choosing the color and size of a pair of shoes. So usually when a manufacturer creates shoes, they make the same color in every single size. It's not like they say, well, I'm just not going to make the purple shoe in a size 7. It might sell out pretty fast, but they usually make it in every single color and single size. So it doesn't really depend on each other. The color doesn't depend on the size of the shoe. So these are going to be independent. Okay. Now, choosing the winner and a runner-up at a dog show. If you have 6 total dogs you're looking at, to choose a winner, you get 1 out of 6. Now, that denominator is going to change because when I'm choosing a runner-up, I now only have 5 to pick from. You can't be a winner and a runner-up. You can't be both. So these are going to be dependent. They're going to be dependent. Choosing a president, vice president, secretary, and treasurer for student council, assuming that a person can only hold one position. That's really big. Person can only hold one position. So if I have 5 people total I'm trying to pick for these positions, I can pick one of them for president. Well, the president cannot be the vice president as well. They can only hold one position. So then I only have 4 people to choose from for vice president, and then 3 for secretary. So my denominator in my probability, my fraction, would be changing. So these are dependent on each other. Dependent. And then last one, selecting a fiction book and a non-fiction book at the library. Well, here's the deal. Fiction books do not depend on non-fiction books. They're completely opposite of each other. So in this situation, this is going to be an independent problem.